Theoretical recap. Integrating security tests into an existing C/CD workflow is the operational heart of DevSecOps. The core principle is simple. Security checks must not be an afterthought bolted onto the end of a pipeline. They must be embedded at every relevant stage. Three families of tests matter here. SAST, Static Application Security Testing, analyzes source code without executing it, catching issues like hard-coded secrets, insecure patterns, or dangerous imports early in the pipeline, ideally at the commit or pull request stage. DAST, Dynamic Application Security Testing, interacts with a running application, simulating an attacker's perspective to find runtime vulnerabilities such as injection flaws or broken authentication. It belongs in staging environments. SCA, Software Composition Analysis, scans third-party dependencies for known CVEs and license issues, and should run whenever dependencies change. A common mistake is placing all security gates at the very end of the pipeline, turning them into release blockers that slow delivery without providing early feedback. Another mistake is treating every finding as a critical blocker. Triage and severity thresholds are essential so that low-severity findings generate warnings without stopping the build. The mental model to retain: map each test type to the pipeline stage where it delivers the best signal-to-noise ratio and the lowest cost to fix. For example, a secret detected by a pre-commit hook costs minutes to fix. The same secret found in production costs weeks. Workshop brief. You have already simulated committing a secret and correcting it, configured a basic pre-commit rule, explored branch policies, and mapped the OWASP Top 10 onto a pipeline. This workshop asks you to go one step further. You will take a provided sample repository that currently has no security instrumentation and deliberately place appropriate security tests at the correct stages of its C/CD workflow. The goal is not just to add tools, it is to justify why each tool belongs where you put it and what it is expected to catch. The sample repository you will work with is a small Python web application hosted on GitHub, or GitLab if you prefer. It uses Flask, has a requirements.txt file listing several dependencies, includes at least one route that accepts user input, and ships with a basic GitHub Actions, or GitLab C, pipeline file that currently only runs linting and unit tests. You are free to fork this repository or replicate the structure locally in your own version-controlled repository. What matters is that you start from a pipeline that has 0 security gates and that you add them yourself. Your work must cover at least 3 distinct pipeline stages. First, at the pre-commit or commit stage, integrate a SAST or secret detection tool. Bandit for Python static analysis and detect secrets or get leaks for secret scanning are reasonable choices. Configure the tool so that it runs automatically and fails the commit or the pipeline step if findings above a defined severity threshold are detected. Document the threshold you chose and explain why. Second, at the pull request or merge request stage, integrate an SCA tool. Safety, Trivy, or Snike in its free tier are all viable. The tool must scan requirements.txt and any other dependency manifest present, and report vulnerabilities. Define a policy. Which severity level triggers a hard block versus a warning? Write that policy down explicitly in your documentation. Third, at the staging or integration stage, add a DAST step. You may use a WASP ZAP in baseline scan mode against a locally running instance of the Flask application, or use any equivalent open-source DAST tool. The DAST step should produce a report artifact that is stored by the pipeline, even if it does not block the build. Justify this design choice. Beyond the technical integration, you are required to produce a short written analysis, 1 to 2 pages, plain text or markdown, that accompanies your pipeline configuration files. This analysis must answer the following questions. What was the existing pipeline missing and why does that matter from a risk perspective? For each security test you added, what category of vulnerability is it designed to detect, and at what stage of the SDLC does it intervene? What trade-offs did you make regarding blocking versus warning behavior, and how did you balance developer experience against security enforcement? Did you encounter any false positives during your tests, and how did you handle them? This written component is as important as the working pipeline. It demonstrates that you understand the reasoning behind the configuration, not just the mechanics. You are encouraged to consult all previous course materials, the OWASP Top 10 overview, the pipeline mapping workshop, the memo sheet on minimal secure pipelines, and the shift left/shift right lesson, as well as any relevant official documentation, blog posts, or tool guides found online. You may work alone or collaborate with peers to discuss approach, but the pipeline configuration files and the written analysis must be your own work. If you get stuck on a specific tool syntax or C configuration, look at the official documentation first. Most of these tools have working example configurations in their README files. A few practical tips to avoid common pitfalls. Start by reading the existing pipeline file carefully before touching anything. so you understand the current job structure and do not break existing steps. Add security jobs incrementally, one at a time, and verify the pipeline runs successfully after each addition before moving to the next. When configuring DAST, make sure the application is actually reachable by the runner before the ZapScan starts. A missing service start step is the most frequent reason DAST jobs fail. For SAST and SCA, always pin the version of the security tool you are using in your pipeline configuration to avoid non-deterministic behavior between runs. You have 10 hours to complete this workshop. Organize your time as follows. Roughly 2 hours to set up the repository fork and understand the existing pipeline, 3 hours to integrate and test all 3 security stages, 2 hours to deliberately introduce a vulnerability or a fake secret into a test branch to verify your gates actually trigger, and 3 hours to write and refine your analysis document. Submit your solution, a link to your repository, public or shared, and your written analysis document, before the deadline expires. Late submissions will not be evaluated.